We ended our last lesson suggesting that we could think about molecular orbitals using only the valence orbitals. So let's think about what this looks like for ethene, our simplest alkene. We can easily see how the red sp2 orbitals come together to make a sigma bond, but pay close attention to how the p orbitals will overlap, not along the lines of the bond, but both above and below the bond. We call this overlap above and below the bond axis pi overlap, and we call the bond created by it a pi bond. When overlap is along the bond axis, a sigma bond, it is much more significant than the overlap created by p orbitals. Because the overlap is low, the stabilization from pi bonding is less significant, and the destabilization from pi antibonding is also less significant. Because pi bonds have little overlap and therefore little stabilization, the electrons in a pi bond tend to be the highest energy electrons, and the pi antibonding orbital tends to be the first open orbital, which you can see in this simplified energy diagram of ethane. The most reactive electrons are the electrons with the highest energy. Molecular orbital theory actually does a great job of predicting many organic interactions based on the energetics of the orbitals that exist versus the orbitals that could exist after a reaction. We talk about the highest energy electrons so much we give them the name highest occupied molecular orbital, which we abbreviate HOMO. The pi star antibonding orbital is often the first empty orbital we come to, or the lowest unoccupied molecular orbital, or LUMO. The HOMO and LUMO tend to be the orbitals that interact between molecules. HOMOs are electron pair donors, or Lewis bases, and LUMOs are electron pair recipients, Lewis acids. To bring this back to molecular structure, this all means that the electrons in a double bond tend to be fairly reactive and will generally donate their electrons to something else when they react. It is important to note that while many hybridized orbitals of an atom will become molecular orbitals, not every atomic orbital has the correct energetics or orientation to form a new molecular orbital. Lone pairs tend to not have formed any molecular orbitals, which makes sense since they don't participate in any bonds. We call them non-bonding orbitals. While they may have been stabilized by some hybridization, like this example where the non-bonding orbitals are sp2 hybridized, they will not increase or decrease in energy from there. For this reason, lone pairs are often even higher in energy than pi bonding electrons, and can often also participate in reactions as the HOMO. We just looked at what happens when sp2 hybridized atoms come together to form a double bond. Now look closely at the atomic orbitals that make up ethine. We obviously get some overlap between the green sp hybridized orbitals along the bond axis, a sigma bond. We also get overlap between the blue py orbitals, just like in ethene, a pi bond. But we also get completely independent overlap between the red pz orbitals along a different plane, a second pi bond. So a single bond is a sigma bond, a double bond is a pi bond and a sigma bond, and a triple bond is two pi bonds and a sigma bond. You can see the overlap again here. Importantly, these pi bond electrons are in completely different planes, and they cannot talk. Electrons in one of these pi orbitals cannot form resonance structures related to the other set of pi orbitals because the orbitals don't talk, they don't interact. Even so, there is no difference in energy between either of the pi bonds. They will now be tied as HOMOs, and their antibonding orbitals will be tied as LUMOs. So again, these electrons are tied for the most reactive electrons. Sigma bonds and pi bonds behave very differently, and this makes a big difference for molecular structure. Sigma bonds have the exact same overlap regardless of what their orientation is, but as soon as you rotate one p orbital relative to another, no overlap occurs and the pi bond is broken. Rotation around a double or triple bond, then, amounts to a reaction. A bond must be broken and reformed. There is a significant energy cost to this. It is possible, but it doesn't happen appreciably at room temperature. So for our purposes, you cannot rotate around a double or triple bond. This leads us to molecules that are connected in all the same ways but are actually separate molecules with different chemical and physical properties. Take these 1,2-dichloroethanes as an example. Each carbon is connected identically to a chlorine, a hydrogen, and doubled to another carbon. But the two molecules have different relative directions for the chlorines. The first has them on the same side, which we call cis same side. The second has the chlorines on opposite sides, which we call trans. These are our first example of stereoisomers, molecules that are connected the same, but in different orientations. Another important gift of molecular orbital theory is that it allows us to think about the shape of orbitals that are around any atom. S orbitals are lower in energy and more compact, and the greater percentage of a hybrid orbital that is made from s orbitals, the more it will be compact like the s orbital. So p orbitals are the least compact, then sp3 orbitals, which are 25% s and 75% p, then sp2 orbitals, which are 33% s, then sp orbitals, which are 50% s, and of course last are s orbitals. The more s character an atom has, the closer the electrons are held. These are functionally more electronegative, so an s orbital can stabilize more negative charge than a p orbital, and everything else in between follows the same trend. sp orbitals are more electronegative, but that also means that an H attached to an sp orbital is easier to remove, since we can more easily stabilize the anion that's left behind. We can alter the acidity of a CH bond from alkanes, which are not at all acidic, to alkenes, which are still not appreciably acidic, to alkynes, which are just barely acidic enough to form a carbanion in really strong bases. That's pretty amazing because we will very rarely see carbanions, and they allow us to form carbon-carbon bonds. As we discussed in this chapter, molecular orbital theory gives us much of the same information obtained from VSEPR theory, but it also allows us to determine information about reactivity that we can never access from VSEPR theory.